My esteemed listeners, today in this session we will discuss one of the famous algorithm design strategies, namely divide and conquer strategy. Divide and conquer is a way of thinking that appears in war winning strategies. Kautilya has predicated, you must all know, 4 war winning strategies. The Sama, the very first step, which proposes the reconciliation or alliances in the event of conflicts. Next comes Dana, that is giving compensation, a huge amount of money in order to avoid the possible conflict. Bheda is the next strategy which is proposed by Kautilya, which is akin to divide and conquer strategy. Bheda here refers to usage of logic or some kind of a trickery, bringing some kind of divisions among the opponent side itself. Danda, the fourth one, is using the force, using armaments to take up the war. Anyway, there are similarities in algorithm design strategies also. Here conquer means getting the solution. Of course, there is no question of any Sama. Sama is not available here in problem solving techniques. Okay, Dana is available, giving compensation. We have a strategy called space trade-off to save the time. We will give away space. Okay, we will discuss whenever it comes. Okay, in the due course of time. It is also one of the strategies, trade-off space against time. Okay, then Bheda is the divide and conquer strategy that is the subject matter of this tutorial. And Danda, I think it appears to me, or it appears to some of you also, it is analogous to brute force technique, because here the Danda is used by the brute, that is a computer, with huge capacity. Okay, however laborious the method may be, however beating about the bush the method may be. Anyway, the divide and conquer strategy includes 3 steps. Divide the problem instance into several subproblems. How long you need to divide? The answer for this question is so long as it is not further divisible. Okay, the problem should not be further divisible. Till then, theoretically, it is possible to divide the problem. For example, if you take an array related problem, and if divide and conquer is the strategy, you can go on dividing the array till the entire array of n elements becomes n arrays with single elements. If sorting is the strategy, any array with single element is already sorted. So one problem is solved. Of course, you will end up in a subproblem which is already found its solution just because of division. Okay, and in some of the cases, okay, it is applicable only for array cases. Okay, the example instance is array, and sorting should be the thing. And in some of the cases, in some of the problems, I think the divide and conquer strategy will divide the problem in such a way that the subproblems are easily amenable for finding the solution. Okay, and if you devise a method for finding the solution for a small problem, subproblem, and it can be recursively applied for all other subproblems, then the third step is a very important step, and we need to integrate, we need to amalgamate the solutions of the small problems into a total solution to the main problem that has arrived us. Okay, we'll take some examples over here, okay, to highlight how exactly in essence the divide and conquer technique is applied. Okay, it is something like this. Let us say we have to sum a, we need to sum, let us say a1 plus up to an minus 1. Let us say we need to sum this. So as far as divide and conquer strategy is concerned, we will divide this into half. Okay, a1 to a floor of n by 2 minus 1, okay, then plus a of ceiling of n by 2 to a n minus 1. So this can be further divided into two parts. This can be further divided into two parts. Okay, that's how it goes on dividing. On the other hand, we can think of another example. That is raising a number to a power. Okay, a to the power of n can always be dealt under divide and conquer strategy to be a to the power of n by 2 to the floor of n by 2 into a to the power of floor of n by 2. Okay, right, this is the division, and this can be further divided n by 4 into n by 4 and n by 4 into n by 4. This can be further divided. Of course, the multiplication is done recursively for the subproblems. This is how it goes. Anyway, it can be seen from the examples that are quoted over here that divide and conquer strategy leads to some kind of double recursion. Okay, that can be seen when we solve the problems. Okay, they lead to double recursion, and we may recall how exactly single recursion moves. Okay, single recursion grows like a chain. We have told this in our previous tutorials. So if a factorial of n is factorial of n minus 1 into n minus 1 into n, and factorial of n minus 1 is factorial of n minus 2 into n, okay, into n minus 1 into n, like this. So it goes on growing like this in one direction. Okay, it is unidirectional, or it grows like a chain. And as far as double recursion is concerned, it goes like this. So a to the power of n by 2 into a to the power of n by 2, and once again it goes like this, a to the power of n by 4 into a to the power of n by 4. Okay, right, a to the power of n by 4. And here one thing that is to be recalled is n should be expressible as a power of 2. That is a basic assumption that we are going to make. Anyway, we will discuss all those things in the future, near future. Okay, like this it grows. Therefore, all the recursive, all the divide and conquer solutions, or all the algorithms will have a way in terms of double recursion, and they grow like a tree. And we can develop a tree of recursive calls. Yeah. Now, the basic divide and conquer recurrence relation. Okay, the basic divide and conquer recurrence relation can be developed, or in other words, simply told, any divide and conquer algorithm should end up in double recursion. Okay, and therefore it ends up in a recurrence relation. Or any algorithm designed using divide and conquer strategy is destined to be a recurrence relation. Therefore, they are not amenable for the analysis under the framework of analysis of algorithms. Anyway, it can be told like this: the running time of the divide and conquer algorithm as a function of input size equal to time required to solve subproblems each of some specific size, plus time required to divide the problem into subproblems and for combining their solutions. Okay, the total time consumed by any algorithm in terms of its running time can be broken into two parts. One is time required to solve the subproblems, okay, small subproblems, and time required to amalgamate the solutions, plus time required to divide, okay, till they are further not divisible. Okay, anyway, a general recurrence relation can be developed with the definition that has been told over here. Okay, the definition that has been written over here. The total time consumed by a recurrence algorithm or recurrent algorithm or a recursive algorithm developed upon using brute force strategy, divide and conquer strategy can be written as, okay, the time required in order to solve a subproblems, each of size n by b, okay, plus the time required as a function of n, time required to divide the problem and also to combine the solutions. In many of the cases, this time is mostly consumed for combining the solutions, because when you go down cutting the problem into pieces, of course at the end some of the problems will show the solutions for themselves. It's only amalgamating the small solutions in array related problems particularly. Otherwise we need to solve the simple problem, small problem, and then we have to integrate the solution. Okay, anyway, I repeat, the total time consumed for any recursive algorithm developed using design and divide and conquer strategy as a function of n can be a breakup of time required to solve the subproblems, each of some specific size, that is a number of subproblems, okay, each of size n by b, plus time required to amalgamate the solutions and also time required to divide the problem. Okay, so once we obtain the recurrence relation after having written the algorithm using divide and conquer strategy, what remains to us is to solve this recurrence relation. And actually we are introduced to one of the methods called as method of iteration or back substitution. Method of tree is not known to us. Anyway, 4 methods are available. Method that uses Master's theorem and guess and verify method. There are 4 methods. Of course, Master's theorem is widely applied, particularly while solving divide and conquer general recurrence or divide and conquer recurrence relation, right? We use Master's theorem. Okay, this is the equation that we have developed upon writing the algorithm, upon analyzing the algorithm. This is the recurrence relation, divide and conquer recurrence relation. So Master's theorem states that if f of n, that is the time consumed for integrating the solutions, plus time consumed for dividing the problem into several subproblems, is if this function belongs to big theta of n to the power of d, where d is greater than or equal to 0 in the above equation, then t of n, time consumed for the divide and conquer algorithm in its totality, should belong to big theta of n to the power of d if this a is less than b to the power of d, or it should belong to big theta of n to the power of d log n if a equal to b to the power of d, or it should be big theta of n to the power of log a to base b if a is greater than b to the power of d. Okay, we will take an example over here, okay, in order to understand this Master's theorem. T of n, let us say some algorithm has given us this recurrence relation. T of n is equal to 4 times T of n by 2 plus n square. Okay, and in every iteration, the meaning of this is 4 problems will be there, 4 subproblems will be there, each of size n by 2. And the complexity of amalgamating the solutions is n square. Okay, so here a equal to n, b equal to 2, clearly a is equal to b to the power of d. Hence, as per the Master's theorem, a equal to b to the power of d. Therefore, as per the Master's theorem, it belongs to big theta of n square, n to the power of d. Okay, d here is 2, n to the power of d, that is n square log n. Okay, so there is no difficulty involved. Okay, thanks to the master. Okay, has given us a ready solution. Okay, if you find the solution to the recurrence relation, previously discussed, as we have previously discussed, it would amount to finding the efficiency case of the algorithm. Okay, another example is chosen. Okay, T of n equal to 2 times T of n by 2 n cube. Okay, there are 2 subproblems in each and every iteration, each of size n by 2, and the complexity of this amalgamating algorithm or integrating algorithm is n to the power of 3 or n cube. So we have f of n equal to n cube, therefore d equal to 3, a equal to 2 and b equal to 2. Clearly a is less than b to the power of d, hence as per Master's theorem, T of n equal to big theta of n cube. Okay, so it falls under second category. So we will take example merge sort as an example. It is the first example and an excellent example for divide and conquer, because we can literally see how exactly array gets divided, okay, before it is sorted out. Okay, the merge sort, of course we have to give respect to the person who has invented this famous algorithm. Okay, with due respects to him, we want to mention. Okay, one of the first sorting algorithms proposed, which is based on divide and conquer principle. This algorithm was written around 1945 by renowned Hungarian mathematician John von Neumann, who is also called father of modern day digital computer. Okay, this is let us be informed about this person. Okay, we will take a merge sort example, and first of all I will explain. Okay, let us understand how exactly this merge sort works, and then we will try to write the algorithm. Okay, so let us consider elements to be 18, 13, 12, 19, okay, 17, 11, 15 and 14. Okay, this is divided exactly at the center. So division is guided by locating the center. I repeat, division in every iteration, okay, is by location, by the position, okay, exactly at the center. If there are odd number of elements, we will take floor of n by 2. So if it is 13, at one place it will be 6, at the other place it will be 7. It is just like that. Okay. Now 18, 13, it will becomes 18 and 13, one place at one side. So it is recursively divided. Once again, double recursion comes to play. Okay, 17, 11, and this is 15 and 14. See here, it was in one array. Now it demanded 4 arrays, small arrays, each of 2 elements. Then 18, 13 is divided once again. We need several arrays now, okay, which each one can carry only one element. This is 12 and 19, 12 and 19, and this is 17 and 11, 2 arrays, okay, and it is 15 and 14. So now we need to stop the division process because it cannot be further divided, and all these arrays subsuming single element are already sorted. Okay, there is no doubt about it. Okay, now we will merging starts here afterwards. Division was there. Okay, division started like this, and we will find the solution somewhere over here. Therefore merge sort is said to have what is called as top-down approach. Therefore here when we merge, we will set up 2 pointers, one I here, the other one is j over here. Okay, I will move in this direction, j will also move in this direction. So now a comparison will happen. Is ai is greater than a of j? Therefore we are arranging things in ascending order. Let us presuppose, therefore a of j should come over here, 13 should come over here, and j cannot further move, it will be there only, it cannot move, and array is exhausted over here, and whatever that remains in the other array should be poured over here. Okay, 13 and 18. Here I is there, j is there. Once again same kind of a trick. We will compare. ai is lesser than aj, therefore 12 will come here, 19 will be there, and here I and j once again. Okay, so a of j is lesser than a of I, therefore 11 will come over here, j cannot further move, so whatever that remains in this array will be poured over here. Okay, now once again same thing is repeat. This is what is called as a recursion. Doing same thing, okay, repeatedly, same kind of thing. Okay, therefore it requires one of the functions to be called again and again. The duty of that particular function is only to merge. 14 and 15. Okay, now these two arrays are taken, and please remember that both the arrays are already sorted. Okay, so I is here, j is over there, I is here, j is over there. Okay, a of I is compared with a of j, so a of j is lesser than a of I, therefore a of j will be seated over here, so 12 comes over here, then j will move. Okay, see the index or the position where element is plucked will be moving. So here from this position 12 is plucked and it is being placed over here, therefore j has to move. Now once again comparison will start. AI will be compared with AJ, and this AI is lesser than AJ, therefore 13 will come over here and I will start move and it will come and sit over here. Okay, j will be there only, stand still. So a of j is compared with a of I is compared with a of j, and a of I is lesser than a of j, therefore 18 will come over here and 19, and whatever that remains in the other array will be poured over here. Once again same trick is played here also. Okay, same thing is executed here also. A of I is compared with a of j, it is lesser, therefore 11 will come and I will move. Okay, once again a of I is compared with a of j will come on, sit over here, it is 14, j will move. Then once again a of I it's over here, a of I is compared with a of j. Okay, a of j is lesser than a of I, 15 will come over here. Then whatever that remains in this portion of the array will be just transferred over here. Okay, this will come and sit over here. Once again there remains two arrays which are sorted already. That is very important thing. Okay, in every merging operation, as we go down towards the total solution, okay, we will get, okay, both sides the sorted arrays. A of I is compared with a of j is lesser, 11 will come over here, j will be set to move and j will come and sit over here. So 12 and 14, once again 12 will come over here, then 13, j will move over here, sorry, I will move over here, then 13 will come, okay, and then it will move. This is 18, this is 14 will come over here, then comes 15 like this, 15, okay, and then 17, okay, after 17 being placed over here, there is no array, there is no element remains over here, therefore this portion of the array exhausts, therefore whatever that remains over here will be just transferred to these empty places, 18 and 19. As you should notice, while merging here in order to obtain the solution, because we start from the sorted arrays, we go on getting the sorted arrays only. Okay, while merging is the operation, and in that merging operation, comparison is the operation. When we have two elements, we have one comparison. When we have four elements, we have three comparisons. When we have 8 elements, we had 7 comparisons. Therefore, when we have n elements in every stage, okay, n element, we will have to have n minus 1 comparisons. We will also remember this, okay, and we will analyze the problem now. We will analyze the problem, okay. We will write the algorithm rather, okay. Algorithm merge sort. The parameter given to is an unsorted array named P. Sorts an array P 0 to n minus 1 by recursive merge sort. Input is an array 0 to n minus 1 of orderable elements, that is not sorted. Okay, array P 0 to n minus 1, the output is which is sorted in ascending order. It returns an array which is ordered in ascending order. Okay, if n is greater than 1, because in order to take up sorting work, at least minimum of 2 elements must be there. Therefore, as long as n is greater than 1, go on copying. Okay, here dividing means copying. Copy the half portion of P, that is P 0 to n floor of n by 2 minus 1. Floor of n by 2 is taken in order to account for odd element arrays. Okay, to Q, this is a new array, empty array, Q 0 to n minus 2, sorry, n by 2 minus 1. And the remaining portion, the remaining elements starting from floor of, floor of n by 2 to n minus 1 will be poured to another empty array R named R 0 to ceiling of n by 2 minus 1. Okay, ceiling of n by 2 minus 1. Okay, merge sort will be called now. Same thing is called. Okay, so this merge sort will once again take to copying or dividing, okay, till n is greater than 1. So whenever, another thing that we have to notice is whenever we have two recursive calls one after the other, okay, the system will finish this first, okay, finish the first recursive call till its base case is reached, then it will take up this one. Anyway, the first one, it would amount to say, first of all, the left tree grows and left tree stops at the tree level, wherein you will find all the sorted elements, and right tree starts to grow. Okay, once again merge sort this thing. Okay, this array is to be divided once again. Okay, then merge operation. Okay, it has to receive single elements and merge operation will start. Okay, now we will continue. Okay, therefore merge sort algorithm should be written in two parts, and here merge QRP is a subroutine or a sub algorithm which is being called by this main algorithm. So main algorithm here is merge sort, and it repeatedly calls merge algorithm in order to merge the solutions. Okay, we will write this also, algorithm merge. So it will involve two subarrays defined by its extremities 0 to m minus 1, okay, 0 to l minus 1, okay. P, the combined array 0 to m plus l minus 1, okay. So here two pieces of array which are sorted already, and this is the combined array which combines this and this in every call. Okay, output and input has been clearly written. We will set the indices now. I equal to 0, okay, which will come to the left sub array, and j equal to 0, which is there poking the right sub array. K equal to 0. This index is for the accumulation of the merged array. Okay, in order to facilitate the accumulation of the merged array. Okay, while I is less than m, because the boundary for I is less than m, for j less than l, okay, it can move up to l, this can move up to m. If b of I, okay, b of I, the element found in the left portion of the array, okay, portion of the array, I think I should have written this as q, okay, q of I is r of j, okay, r of j, then p of k equal to q of I. Okay, if q of I is less than r of j, then p of k, that is merged array, should receive whatever that is there in q of I. So I equal to I plus 1, I should move, because from this array we have plucked the element, right? Then else p of k should receive element, whatever the element that remains in r of j, j will be moved to j plus 1. J will be moved to j plus 1. So k equal to k plus 1. This is in order to facilitate next new cell for p. So it is incrementing the indices of array p. Okay. Okay. If one of the arrays gets exhausted after picking up the elements from that particular array, let us say I will reach m, because it will go up to less than m. Okay, once it gets incremented after filling, it becomes m, it has to come out, because both the conditions should be satisfied in order to make this particular while loop to work. Therefore, if I gets exhausted, see the array q gets exhausted, okay, then I will be equal to m. Then in that case you have to copy whatever that remains in r. P R, actually this is R, whatever that remains in R. Otherwise you copy to B to P whatever that remains in Q, okay. So this is the thing. So now every time it calls till this particular condition is not met with, okay, when the complete merging happens. Now we need to develop a recurrence relation for the algorithm in its worst case. Okay, it is written over here. The time taken by the merge sort algorithm till it finds the final solution. Under the worst case is, so in every time as much of time as it is required to solve two subproblems, each of size n by 2. I repeat, it is as much time as it is required in order to solve two subproblems, each of size n by 2, and n minus 1 comparisons for merging. In every step we noticed it requires n minus 1 comparisons for n greater than 1, okay, and time required for one element, if at all input size is 1, is 0, because there is no sorting at all. Okay, here applying Master's theorem, here a equal to 2, b equal to 2, and d equal to 1, because n to the power of d, n to the power of 1, therefore d equal to 1, a equal to 2, okay, two subproblems in every stage, okay, each of size n by 2, whatever the n that remains in that particular stage, okay. So d equal to 1, therefore a equal to b to the power of d, which corresponds to the second case of Master's theorem, which states, okay, the total time required by the merge sort algorithm in its worst cases belongs to big theta of n to the power of d log n, here d equal to 1, therefore the complexity happens to be n log n complexity, okay. Though it may seem that n log n, for example, if there are 100 inputs, let us say 100 elements, the meaning of this is approximate number of comparisons that happens in merge sort algorithm is 100 into log 100 to base 2. Of course, log 100 to base 2 happens to be somewhere around 33.33, let us say 33.33. So okay, therefore it is n into, that is 100 into 33.33, okay. It is so less, but however we have to say despite its moderate time complexity, merge sort n log n is when compared to quadratic complexity like bubble sort and selection sort, wherein number of comparisons will be 10,000, okay. Here it is very meager, okay. 2 to the power of let us say, yeah, this is n means 100, log n means once again 33.3, okay. So therefore despite its moderate time complexity, merge sort performance gets degraded when the input size decreases during the division phase, because it has to satisfy the overhead of creating, working with and destroying many small arrays. It has to generate small arrays, empty arrays, once again it has to destroy, it has to copy. There are so many extraneous procedures that will take place, and those extraneous procedures are time consumed. For enforcing those extraneous processes is not accounted in this complexity. That is a problem. Okay. Anyway, basically, by de facto standard is merge sort has efficiency case of n log n. Okay, right. Yeah, this is the definition of how exactly we wrote this. Okay, total number of comparisons that occur in merge sort. Okay, MERG merge sort is equal to total number of comparisons during divide stage to form two subproblems of size n by 2 each, and n minus 1 comparisons while merging the subarrays, right. And there are some problems given here, and our esteemed listeners, okay, I will definitely try to solve this. Anyway, I will try to give the clue also. Write a divide and conquer based pseudocode for finding position of the largest element in the given array. Okay, I don't write the complete array. Okay, you can fill up, but I will try to give you some kind of a clue. Okay, the base case for this is let us say if I am answering the first question, if let us say L equal to R, that is one element array is given to us, then we have to return L. Okay, it is returning the index. Okay, whatever the element comes, it is a single element, therefore it is the thing, that is the thing that is to be transferred. Else we will have two variables now, else, okay, we have to divide the array. T1 equal to let us the name of the algorithm is max position. Okay, finding max position. Okay, max position. okay, and the array is A lower boundary 2 what is the other thing, the end thing, the last element is L plus R, that is lower boundary or left extremity and right extremity divided by 2 and the floor. Okay, this is to account for odd numbered element array. Then what remains with T2 is, what goes to T2 is the maximum among the other half of the array. So maximum position that is obtained for this array A, okay, it will start from, once again, from L plus R by 2 floor plus 1 etc to R, the right extremity. Okay, so upon completion of these two recursive calls, what we get is the maximum among half of the array, that is and maximum among the other half of the array. We will compare that. Okay, if A of T1 is greater than or equal to A of T2, then we will return A of T1, okay, return T1, okay, as the index where maximum valued element is present, else we will return T2, okay, return T2. This is the thing. Next another, of course, arrange the alphabets of selection sort in alphabetical order using merge sort. Okay, you have to divide this. You can use the cardinal number of each and every alphabet, and you can make it a array consisting of integer numbers, and you can do the way in which we explained the merge sort to start with. Okay, now the other one is write a pseudocode for divide and conquer algorithm for finding a to the power of n, where n is a positive integer. It can be thought of like this, and my esteemed listeners may solve in other way also. This is not the only way. Anyway, this is my bit of mind. Okay, I am giving it to you. Algorithm. Okay, let us say divide and conquer power. Let us say DCP means divide and conquer power. For want of time, I am just telling this. You can give appropriate name to this function so that it will give a notion of what exactly it is doing. Okay, that you will do. Okay, A comma n, the array and n, two parameters are to be given. Anyway, for this algorithm, okay, if n equal to 1, then it becomes a to the power of 1, return a. Now division comes into picture. Okay, this is the base case, return a. Else return, I think you must be assuming by the point of time as I explain here, else return the half of the power raised to half of this thing. Okay, DCP, that particular number, half power, DCP, okay, a to the power of floor of n by 2 into a to the power of DCP, the function should be there. Of course, it's a recursive call, we can't afford to forget this. Okay, to the power of ceiling of n by 2. Okay, this will address even if the problem is odd numbered index. Okay, the appropriately, as you might have guessed, multiplication is the thing here. Over here, multiplication is the thing. Okay, 2 times number of multiplications as a function of n equal to as many multiplications as it is needed to find a to the power of n by 2, plus, okay, another as many multiplications as it is needed to find a to the power of ceiling of n by 2, and plus one multiplication that happens over here. As many multiplications as it is needed to rise a to the power of n by 2, and as many multiplication as it is needed to find a to the power of another n by 2 plus 1 multiplication. And of course this can be solved by assuming n equal to 2 to the power of k. That is the smoothness rule that we explained in the previous chapter itself. Okay, so with this we conclude an elaborate explanation for merge sort and an introduction to divide and conquer technique. Okay, we will come out with quick sort, another famous example for divide and conquer technique, in our next tutorial. Until then, bye.